right, so sketch the region whose area is given by this lovely iterated integral, also called a double integral. Why do you think it's called a double integral? Because there's no arrow. All right, so now notice in this problem, first thing I was hoping would throw you is that I asked for area, or I mentioned area and not volume. Yesterday, we did all these iterated integrals, and we did them all to calculate volume, right?
Yeah.
So what we said was, these boundaries determine the boundary of the region in the xy plane, and then your z is the height of your prisms that you're adding all together, right? Okay, so what is our z value here? It's 1, right? Because, there's no other function listed, it's just 1. So if you have any type of a 3D shape with some base and a height of 1, the volume is the same as the area, right? Because it's just area of the base times 1, right? So the volume would be the same as the area. So when you have a double integral, then it's not that there's no function, it's that the function is just 1, right? Then you're actually kind of finding both. You're finding the area of the bounded region on the xy plane, or you're finding a volume of a shape with that base area and a height of 1, because they would be interchangeable. All right, so sketch the region whose area is given by this. So everyone knew that x equals y squared was a sideways parabola. So well done, those of you who drew a sideways parabola. There's my sideways parabola. But let's just talk about, a lot of you cut off the top. So I'm a little confused on why you all thought that x or y equals 2, sliced off the top here, because I'm pretty sure that you know that 2 squared is 4, right? So, yeah, something went awry on several of these graphs. So, anyway, yeah, we just got confused. Okay. So anyway, so this is the graph. This is the region we're talking about, right? Now, I actually have the answer here, which I don't really want to show you. Let's just talk about it first. Okay. So if this is our region, remember, for this integral, so this is x equals y squared, x equals 4, from y equals 0 to y equals 2, right? Okay. If we want to reverse it, last year, when we reversed doing area, doing a left-right instead of an up-down, so we have to solve, if this function right here, if this is the function x equals y squared, then we have to solve it for y in terms of x. So this would also be written as y equals, this top part would just be positive root x, right? The bottom would be negative root x. Okay. So you could use either one of these to represent this curve right here. So when we do our rewrite of our integral, and this is what our focus is on today, is double integrals where we reverse the limits. So when we rewrite our integral, here's what you think. So this is dx dy, so we're going to do dy dx. So first we look at our y values. So you think like low to high. So our bottom y value, and remember these are kind of functions and these are constants, like starting and ending values. So our bottom function, this guy right here, that's y equals 0. Our top function, that's this guy right here, that's y equals root x. Then you ask yourself, starting and ending x values. I'm starting at x equals 0. I'm ending at x equals 4. Every single time I have to change an order of integration, I always have to draw a picture. I don't know if that's a failing on my part, but that is just what I have to do. Like my brain will not do it without a picture. So for me, every time I have to reverse order of integration, for me, I sketch the region first, and then I just kind of redefine my functions the other order. So remember that your outer integral is always going to be numbers, starting and ending values for that variable. The inner one is going to be like the definition of your curves, your boundaries. Okay, in today, but there was a slide we skipped yesterday that I might go back and make this do. Yes. Sir.
Can you do double
Yeah, you can do a double indefinite integral. You just wouldn't have anything to plug in. You would anti-differentiate with respect to one variable and then anti-differentiate again with respect to the other variable. Yeah. Okay, so today we're doing 15.2, order of integration. Learning targets. I can change the order of integration of an iterated integral, and I can find the area of a plane region using multiple iterated integrals, because we're going to get into some where we might have to split things up today. That's my little, like, starty, stoppy recording thing.
Oh, it's behind the leaf. It's like behind the leaf right there.
It's behind the leaf? Oh, there it is. Oh, thank you. Wow, I never would have seen that. Okay. There is, that I know of, there is no quick and easy method for reversing the order of integrals. You can't just change the letters and move the stuff around and have a new integral. By the way, well done. It just doesn't work that way. What, do you guys want a well done too? You guys, well, I could congratulate you guys before you started talking about it, right? So, no. Yeah, there we go. Well done. Okay, so we have 3 groups. Okay. So anyway, so just like last year in chapter 7, I don't know if you remember this or not, but when you have a region, if I have a region, say I'm doing a region like this, right? So this kind of a region. Well, if I do this top minus bottom, it's really easy. It's, you know, this function minus this function. But if I'm doing it right minus left, I have a problem because I have 2 different functions on the left. So this minus this and this minus this. So when you have multiple, like, different functions that on the same side of your integral, you have to split the integral into multiple integrals. So that's what I'm talking about here when you have to split the region into multiple integrals. All right. So, for example, sketch the region of integration for the iterated integral below and then switch the order. So now we have a function here, but they don't tell you what it is. It doesn't matter. It's just any generic function in terms of x and y. What matters when you're switching the order is this stuff, is the limits. This has no relevance when it comes to reversing the order. Z is Z. Yes?
So the function, that's just like your z values, right?
Exactly.
So if you draw that, that's just like the base.
Yes, that's in the xy plane, the region that you are integrating over. So those are, it's like the set of all ordered pairs you're plugging into Z.
Okay.
All right, so take a second and just see if you can sketch a quick graph of what this looks like.
Do we get calculators for this?
No.
Oh, that's so sad.
I know.
Are you going to give us
Any graphs that are tricky at all, I have pre-printed on the test. For this test, for the last 2 times I taught the class, the graph was not the downfall.
What if it is?
Well, I mean, anything's possible.
Yeah.
Like right here, then. I forgot how to graph one of these.
No, it's, oh, e to the negative x. So e to the x goes like this. E to the negative x goes like that. It's literally e to the x reflected over the y-axis. Oh, that's why I had this stuff covered up, so you couldn't see it. So there's my graph. So I have e to the negative x. So y goes from 0, which is the x-axis, to e to the negative x, which is this swoop. And then your x's go from -1 to 2. So here's the problem. Doing it dy dx is really easy. It's a simple top minus bottom. Doing it dx dy is a little bit harder because see this little like line right here? We have two different functions on the right-hand side. So we have to actually split the integral and do one integral from 0 to whatever this number is of this minus this, and then another integral from here to here of this minus that. Or I guess I should stop saying minus, I'm in AP mode, of from this to this, right? So one from here to here, here to here, and one from here to here, here to here. So you're going to need two integrals. So now, absolutely, you can, well, do you really need to use it? No, you don't need a calculator. Just finding that intersection, just plug in the two, right? So take a minute in your groups, discuss, see if you can figure out how to rewrite this, a double integral dx dy that will give you the area of this region. Okay, so when you're building this, and you have to, when you're doing this with double integrals, so now we have like this, I hate this, I've got to, someday, it's never going to happen. Someday I will actually get used to starting over with the recording. All right, so this is y equals e to the negative x, and this is y equals 0. Now, if we're going to go kind of switch and have our functions be more of a left and right thing, so our x's are now driving it, I got to solve this for x. So I take natural log of both sides. So I get ln y equals negative x. So x equals negative ln y. So that's this function. This function is pretty straightforward. This is just x equals 2. And this function is easy. It's just x equals -1, I have to put 0. -1. All right, so we got all our x functions. We need our y values. We need this guy and this guy. Well, the height of this guy is actually this height over here, which is what you get when you plug 2 into e to the negative x. So this is y equals e to the negative second. I should probably do this in a different color. And then this one is what you get when you plug -1 into e to the negative x. So you get y equals e. So your first integral, after labeling all that stuff, your first integral, you would have x equals -1 to x equals 2, y equals 0 to y equals e to the negative second. So your first integral, oh, that's my second integral. Shoot. Let's pretend that one, you can't see that. Okay, so x equals -1 to x equals 2, y equals 0 to y equals e to the negative second. So now you're doing your x's, like your x boundaries first. Then you move to the second part from here up. And so now your x goes from -1 to negative ln y, and your y goes from e to the negative second to e. Remember when you're writing a double integral, the inside integral, those are kind of your function boundaries. the outside integral has to always have numeric values for the limits. So it's kind of like a starting and stopping value. Michelle, you look stumped. Are you okay? Danny, how you doing? Okay. Yes, Tejesh?
So a quick question. It's like, why are we doing this? Like, why can't we just do like top minus bottom be over with?
Okay, that's a fair question.
I'm confused as to, like,
So this is just to teach you how to reverse the order on a complicated problem. You're right. To find the area, or to find the volume, because there's a function here, to find the volume where this is your bounded region in the xy plane, the easiest way to do it would just be to do it dy dx and be done, right? However, there are times when converting to dx dy is to your advantage. One of the times, which you will learn and will be tested on, is if you hit a double integral and you have a function, an integrand, that you can't anti-differentiate. It just doesn't work. And so with respect to whatever variable you've got, right? But if you reverse the limits and anti-differentiate with respect to the other variable, then you can do it, right? So you do it with respect to the other variable, that changes the function, and then you can actually end up completing the integral. So that's when reversing the order is not just like interesting but necessary, is when you have to do it in order to anti-differentiate. Dorsey, do you have a question?
I'm trying to understand like the picture. Like the.
I know it's so messy, I'm sorry. Do you want me to erase all this and start clean?
I don't know.
Here. Let me erase this. I'm going to delete this.
I'm trying to see like how there's like boundary like compared to the picture.
Oh, this whole thing's connected. All right, I'm going to redraw it. Because for Mall, what I did was I actually drew it with a little bit more space so it was easier to see. Like that. Okay, so this is y equals e to the negative x, y equals 0. All right, and the region that we're integrating over is that. Okay, if I was doing this dy dx, then I would have y goes from something to something, right? So lower boundary is 0, upper boundary is e to the negative x. X, beginning x value is -1, ending x value is 2. Done, right? That's dy dx. If I'm going to go dx dy, then instead of doing upper and lower boundaries, I have to do left and right boundaries. When I do left and right boundaries, I have 2 different boundaries on the right-hand side. Like if I were to draw a line connecting left to right, if I drew it up here, I'd hit this guy. But if I drew it down here, I'd hit this guy. Since I have 2 different boundaries on the right-hand side, I got to do 2 sets of integrals and add them together. So the first integral is just I'm just going to do this rectangle. All right? Okay. So if I just do the rectangle, all right. So just looking at that rectangle, x, what is my left x value? -1. What's my right x value? 2. All right. My y, what's my lower y value? 0. I need this value right here.
I'll just plug in like -1 or 2.
So it's going to be determined by wherever y equals e to the negative x intersects x equals 2, right? So I just plug 2 into my function, and you get y equals e to the negative 2nd. Okay. that help?
Yeah.
Okay. Now, plus. Okay, we got to do it again for this part up here. Okay, so here's the problem. When I do my, well, okay, the x value on the left. X value on the left is easy. What's the x value on the left? Still -1. But now the x value on the right is a function. It's not a constant, right? It's curved. So we have to solve this for x.
That's what we got.
Yes. So I solve for x. I get x equals -ln y. And that's going to be my new other boundary. So -ln y. All right. For that part of the graph, what's the lower y value?
The red one.
The red line, which is what y value? Yeah, you can say it. E to the -2nd. This upper y value right up here, well, that's where x equals -1 intersects this function, right? So this is e to the negative first, or just e. So then I'm going e to the -2nd to e. And now I have integrals that will cover the whole thing. Does that help? I know that was for Dorsa, but I'm hoping that helps several. Yeah? Okay. All right. Good. Okay. Lots of thrills with integration skills. This is a nod to my old geometry teacher. So, did I ever tell you about my old geometry teacher? His name was Coach Glover. He was our head football coach. He also taught geometry. And he was kind of funny. He was a big guy. And we would start, I can't remember, it was like one day a week. And he would say, it's time for, and then we would all have to chant, lots of thrills with basic skills, right? So I remember doing that when I was, I don't know, 13. So, and with my geometry teacher, Coach Glover. All right, so lots of thrills with integration skills. For each iterated integral below, I want you to, switch the order of integration and then evaluate. You can evaluate with either one. I don't care which one, whichever one's easier is fine. But I want you to switch the order and evaluate for all 5. So I'm going to have, wait.
Yeah.
There we go. Let me make this a 10. Do you really want this up? Don't you want to work a little bit on paper? How about this? All right, I'll make a deal. You guys do 1 and 2 independently on paper, and then 3, 4, and 5 on your whiteboards. All right? I'm going to make this a little bit bigger so you can see it better. And move this over. There. So for our first one, I don't have a picture drawn. I'm going to quick draw a picture. You've got to be careful. So remember, this is y equals x. This is y equals 3. Your graph has to be in between all of these boundaries, right? So I saw a lot of people saying, oh, my x goes from 0 to 3, and graphing down here. This would be y equals 0 to y equals x, not y equals x to y equals 3. The graph is actually up here, so make sure you shade the right area, right? Okay, and then to reverse it, now we're going kind of left to right, so x equals 0 to x equals y. Lowest y is 0, highest y is 3. Okay. All right, so for the next one, this one had everybody having a lot of fun, right? So cosine looks like that. From negative pi halves to pi halves, we get that lovely figure. So what I was telling people was, if it's bothering you to do the negative arc cosine to the positive arc cosine, if that freaks you out, then just do this area and double it, right? So just go from 0 to arc cosine y, and then y goes from 0 to 1. and then just double it. Yeah, Aubrey.
How do you know that y goes from 0 to 1 and not like y equals 0 up to the next?
Oh, okay. So you're this to turn. Okay, that's a good question. So let me say this in another way and see if this helps it make sense. So in order to produce all of the ordered pairs, we are taking all the y values from 0 to cosine x, and we're plugging in all x values between negative pi halves and pi halves. And that'll generate all the ordered pairs. Going in reverse, so we're going from this function to this function, from this function to this function, but what numbers do we plug in? We plug in all the y values starting at 0 and ending at 1 in order to generate all these ordered pairs.
The outside one is always 2 numbers.
Outside one's always 2 numbers. Yes, it's the lowest number you would plug in up to the highest number you would plug in. Yes, good. Any other questions on that one? All right, wow, we are like ready to go. If you want to check any answer, I'll go ahead and put these up.